Yeah, so again, a very warm welcome from my side to everyone who joined today. Yeah, some of you already know me, or most of you know me. My name is Angela, and I'm responsible for marketing at AppWorks. And I also think that almost everyone knows AppWorks, but just a short summary, let's say what we do and who we are. So we are a 100% subsidiary of Premium Aerotech and part of Airbus, and we design, develop, and manufacture products which exploit the benefits of additive manufacturing. And as every week, before handing over to John, some technical remarks. So whenever you have questions during the presentation, type them in the Q&A session you see below. And after John's presentation, we will answer all of them if time lasts, and if not, get back to them afterwards. Yeah, so just a quick intro. So it's time again for all of you to grab your coffee, lean back, and listen to John.
Sorry. Hey. So hi everyone. I'm John Meyer. So I'm the Chief Product Officer at AppWorks, and today I'm going to talk to you about Scalmalloy. And we maybe use the rather provocative title for in the advertising at least, which was you know, Scalmalloy is way too expensive, right? And I think this is let's say for those of us who like to think about how complex things can get sometimes when you're in engineering, design to cost and so on. It's maybe a tongue-in-cheek phrase, and what I want to talk to you today is about a little case study we did, just to show how important design for manufacturing is in the case of additive manufacturing, and how that can affect, let's say, the value of improved material properties, for example, on the cost of a product ultimately. So, for those of you not familiar with Scalmalloy, it was actually an invention of Airbus Group, so developed by colleagues in the Centre for Research and Technology of Airbus, and then commercialized by AppWorks. So we have made sure that there's a supply chain for the material. It's quite widespread, relatively, application within additive today. And the material main benefits are that it has a very high mechanical properties. And we'd say it's the first material that was really developed specifically for additive manufacturing, as in the particular composition of the material just didn't exist before, because it would not be easy to process by other means. And there are plenty of examples on the screen just to show you applications of the material. But maybe to dig in why Scalmalloy is beneficial to use in design, just to touch on some points, not all of which are considered in the design study we talk about. So the one that is considered is, of course, the high strength. And the uniqueness, I would say, is the high strength coupled with excellent ductility. Typically in plate materials, for example, aluminium alloys, when you end up machining any kind of meaningful part out, you're dealing with quite thick plates. And when you roll thick plates, not only do you have a residual stress profile through the plate, but also you tend to get larger grains in the middle and poorer properties and quite directional properties. So the highest strength aluminium alloys from you know, rolled plate or extrusion or forging, yes, they have very high properties, but typically they're quite anisotropic, so stronger in one direction than another. And often, while the elongation or ductility is quite good in one direction, in the primary direction, if you go into the short transverse direction, often they have very low ductility, so quite brittle behavior. And this can be quite challenging, not just from a static design point of view, but actually when you start to get into things like corrosion, behavior because of grain boundaries, and fatigue, and the relationship between corrosion and fatigue. Scalmalloy also benefits as it has a magnesium basis to it with good corrosion resistance. So it behaves like a 5000 series aluminium alloy, which is to say it has quite good corrosion resistance for an aluminium alloy. And coupled with the strength, it's quite unique in that respect. It has good weldability. Obviously, that's important for additive. it's important to say that cooling rate is important to the material properties, but we find that welding the material after even to assemble additive manufactured parts results in good results. So we don't see cracking and things like that in welding, and we still see good material properties after weld. We have, very importantly, a stable microstructure at high temperatures, up to 250 degrees. So it's not a case that you see an aging effect or an ongoing aging effect in service, if, as you might see with aluminium silicon alloys, where you typically have to artificially age them to avoid that effect. With Scalmalloy, we do one heat treatment process, which effectively achieves a full strengthening, and there's no subsequent aging at exposure to temperature. And that's obviously important if you want reliable material properties in service, where you're seeing any kind of elevated temperature. And with some aluminium alloys, you can even get aging at room temperature. You're also having the advantage that to achieve that does not involve a very high temperature heat treatment and quenching cycle, for example, as might be the case with a T6 heat treatment of aluminium silicon 10. So this avoids a lot of issues you might see around distortion, because it's one thing to print the thing the right shape, but if you have to then perform a special heat treatment to achieve a stable microstructure, which involves a quenching step, for a lot of geometries that will introduce a distortion, which if you're going very near net shape can be really challenging to cope with through design. And then, I mean, it machines normally. I guess the question people often ask is, it's very strong, it's very tough. Is it hard to machine? Not noticeably. And it's also possible to anodize, another question people often ask. So we have a lot of applications where we're anodizing to get either a harder wearing surface or improved corrosion resistance. So how does it work? I haven't really mentioned yet the chemistry that really makes it work, and that's the scandium addition. So scandium is kind of a magic element, which a lot of material scientists love the effect of scandium with aluminium, in that a very, very small amount of scandium has a very, very big strengthening effect on aluminium alloys. The problem that you have with this is scandium is very expensive, so you can only really afford to put a small amount in. And if you put a lot of scandium into an alloy, you need to have a very high cooling rate in order to avoid the scandium coming out of solution. So this is where it works very well with additive manufacturing, with laser additive manufacturing, because you have a very small melt pool with cooling rates of the order of, you know, you're talking millions of degree Kelvin per second, rather than hundreds of degrees per second or something like that in a bigger melt pool. And this enables you to maintain this supersaturated solid solution of Al3 scandium. I'm not a chemist. You're then performing an aging heat treatment, which is leading to this precipitation of these nanoscale particles. And it's kind of weird. It looks like a night sky if you look at it. In an SEM image, you see all these tiny, tiny little pinpricks of these precipitates, which are nicely dispersed because they have been maintained in the supersaturated solution. And this is giving you these, let's say, dislocation obstacles, which are giving you this very high strength. And as I said, the beauty there is high strength with ductility. But the reason no one thought of doing this before is if you just try to cast this material, for example, with low cooling rates, you would simply have a material full of large defects that would actually act against you. So it really does rely on the cooling rates of additive manufacturing. To compare the material properties just to a few alloys, so I just picked a few. So 7075 T6 is a kind of fairly high strength plate material. You can see very high UTS. But also high density. Scalmalloy has a reasonable quantity of magnesium in the alloy, and this is bringing the density down a little bit. So it has the same density as aluminium silicon 10 or A357 if you're familiar with casting. But it has strength values, and particularly yield strength, which is of course very important for design, which is really up there in the range of a 7000 series alloy, and with ductility that is up there in the range of the good direction for a 7000 series alloy. So its specific properties are very, very close. If you see here, 170, so specific being the yield strength divided by the density, and you get something that is comparable then as a rough rule of thumb for design. And you can see it's very much in that range. Another advantage of having these high properties that's often overlooked, if you think, well, I just want to replace a casting, why do I need high properties? Is in fact, you can use these properties in two ways. Either you can optimize design to save weight, if that's what you're interested in. But you could also use the larger safety factor that you have from having these higher properties to reduce cost in non-destructive testing. And there are, I won't direct you to the paragraphs and lines, but there are plenty of provisions in most certification requirements that, depending upon, including the aerospace ones, that depending upon the margin that you apply for certain classifications of parts, how much non-destructive testing you have to do. So do you eliminate X-ray, for example? In some cases, you can eliminate X-ray by having a big enough margin of safety as you would get from swapping A357 casting for a Scalmalloy AM part. And that's, of course, a cost optimization. Today, I'm going to focus more on the design for AM aspect, so how you can, by design, improve the cost effectiveness. The real thing, and most of you are probably familiar with additive, is part cost in additive has a very high sensitivity to the part volume and the bounding box volume to a secondary degree. So you're melting material, that takes time. Your build time is proportional to how much material you melt to make the part. And of course, you're amortizing the cost of a very expensive piece of equipment as you're using it. So essentially, rough rule of thumb, the heavier the part or the more volumetric the part, the more expensive it will be. And actually, I've used volume there rather than mass, because actually, even if you change material, volume does seem to be an important driver more than mass. It's about how much energy you have to put in to melt the part. And that's a multitude of factors go in there, but volume is not a bad metric, even if you compare quite different materials. The part cost has a relatively low sensitivity to geometric complexity. It's not true to say there's no added cost of complexity with AM, as people often claim. It's a bit of an exaggeration, but it's a very low sensitivity to that compared to other processes you might consider. And therefore, doing an optimization, yes, you have to invest in design, but the fact that the final geometry looks more complex doesn't necessarily relate to a more costly manufacturing process. And as I will show in the presentation, often it can lead to a cheaper manufacturing process because you have less volume in the part. The other reason to design for AM is, of course, if you optimize your design for the process rather than simply substituting a part that was designed for casting with one printed by AM to the same design, is you can eliminate a lot of support structures. And of course, those support structures are also volume that you have to print, and therefore they come into the cost equation. So the more you can get rid of them, the more cost you can get out. And generally speaking, if you design for the process, you can really improve that. So the point being that raw material cost doesn't necessarily mean higher part cost. If you have a powder that's more expensive, it doesn't mean the part will be more expensive. It's a question of not just how much less material do you use and therefore how much less powder do you buy, but it's even a factor of how much less, more critically, of how much less machine time you use, which is something which is somehow, let's say, independent of the material price. So bearing all that in mind, we did a little study, and we actually did this last year, but it's good to bring it out again. We did a little study in collaboration with Paramatters, who are a great company I'd recommend you to look at in California, who are doing topology optimization on a pay-per-use basis. So with the web-based tool, it's really evolved over time. It's very, very good. So we did a study with them where we defined a non-design space for a brake caliper. This was just chosen as an example. It's not saying that this is something we should do or would do. It's just to take something where we understand the loads and boundary conditions. So we set up an optimization, and the idea was to run that optimization for 3 different materials. We didn't want to just compare aluminium silicon 10 to Scalmalloy, because we knew that people would immediately say, aha, but what about titanium? Because maybe I could switch to titanium for this part, give or take all other design considerations. So we did that as well, as it's a very commonly used alloy, to really see this effect of a much higher strength but higher density material into the mix. And then the goal was to evaluate, with respect to cost and mass, the result. So there's Paramatters' website there if you want to have a look. I recommend it. So we fixed the design space and the loads and boundary conditions. Basically, we fixed the problem as to what it was, and we ran through the Parameter software the 3 different material options that we have there by feeding them the appropriate material properties. And in parallel, what we did is we also did the AM cost estimation. So we did the build time simulation. First, we did orientation optimization, support generation, and we applied the material process parameters to get the build time estimation, material waste, using a cost model that we've developed, which some of you might be familiar with, AM Expert. And out of this, we get a mass and a cost. So you can maybe see where I'm going with this is, of course, this is a classic Pareto problem where you're saying it's a trade-off, right? Normally, mass and cost is a trade-off. Lighter part, more expensive would be the traditional approach. These were the assumptions we put into the model. You can glance at this. I'm running a bit over time, so I won't spend too much dwelling on it. But you can see the main point being that, in fact, we assumed the highest powder cost for Scalmalloy, which is, to be honest, higher than current market price, I would say, if you go and get a quote. But we were trying to be as pessimistic as possible on the price because we didn't want to undermine our own argument. We have titanium 6.4 and we have ALSI 10 example pricing. We could change this and see what effect it has in the model if anyone really wants to dig in. And these are the optimization results that we got. And what you'll notice is that they firstly look quite different. So the aluminum silicon 10 solution looks really completely different to the other 2 because it's running into, to meet the stiffness requirement, it's running into the edge of the design space and having to fill that space with material, which is a good indicator that it's unlikely to be an efficient design or as efficient as a design that is less constrained by the design space. With titanium 6.4, you can see it's very spindly, so it's a much more spindly design because we have higher specific properties. Of course, we're running a much higher stress, but we have a much higher yield stress to play with, a much higher design value. And they're at a lower mass. What was interesting and actually not entirely expected, to be honest, when we started the study, was that Scalmalloy would be lighter than Ti 6.4. We expected, based on specific properties, that the Ti 6.4 solution might be a bit lighter, that they would be similar. And what we concluded was that this was mainly driven by the non-design space. So all these features, in this case, these cylinders for the pistons, which are mandatory. So let's say anything where you just can't topology optimize it, you need that feature. Of course, a lower density material, if you're limited by a particular feature geometry, you might call it parasitic mass or whatever you want to call it. Of course, there's less mass in those features when you have a lower density material. So that is also a factor to consider. If you have a part where it can completely be optimized and there's no parasitic mass, then titanium might give you a lighter solution. But at least in my experience, almost all parts have some degree of parasitic mass that you cannot optimize away from a stress point of view because there are other requirements. And that's what leads to the slightly lighter solution for the Scalmalloy solution. You notice they all have quite a factor of safety if you memorize the figures from the previous page, and they're all almost identical factors of safety. This was built into the optimization. So they all achieved a converged optimization with a similar factor of safety to within a tolerance that we accepted. So in terms of mass, it's pretty clear. We compare the baseline design, which was say the design based on identical models, the same geometries and visualization solution lighter as shown on this slide. Where it gets interesting, of course, you have to tell acid manifold aluminium if you
And your connection is a bit
Hi, sorry. When did I break down?
With the last slide, it got bad basically connection wise.
Okay, let me share it and I will try and talk through it again. Sorry about that, everyone.
Restart with this one, it would be perfect.
With this one here?
With the one before.
This one here. Okay, this was just talking through the results on the mass. It's more or less reiterating what was before, but just to say we compared also a milled aluminium baseline to all of these additive manufactured solutions. So the mass of the milled baseline is the same as the ALSI 10 baseline, which was basically the design space that was given. So this was the extent in which we could operate. Imagine you're substituting a part and you need to conform to the same space allocation. So the masses of these are the same, and you can see, as shown in the previous one, the Scalmalloy one is the lightest, titanium 64 is a little bit heavier, ALSI 10 is quite a bit heavier, 3 times the mass roughly of the Scalmalloy part, for a similar degree of optimization, so really like for like. If we look at cost, this is where it gets much more interesting. So with, I said, milled aluminium part, in general, if you're talking about a relatively simple geometry to machine, as this case, without lots of secondary processes and so on, and complexity, it's unlikely to be cheaper than printing the same part in AM, for aluminium particularly the case. So you need to have a good reason to use aluminium in the first place, and there are plenty of good reasons, including that you're dealing with an obsolescent casting, for example, a supplier that's missing the supply chain, or you're dealing, in the case of an optimized design, with something where you have very complex design, and actually it starts to become an assembly if you avoid AM. If you go for milling, and you possibly start to look at milling, brazing, several operations, and for sure it makes sense. In this case, what we want to show is if you just print that same geometry, so someone just picks up that CAD model and sends it to someone and said, please print it, I mean, the cost is eye-watering, and many of you may have experienced this. If you take certain parts and you send them, you say, hey, especially a bulky part like a brake caliper, a conventional design, say, hey, that is seriously expensive. This technology can never work. Now, if you work your way through the optimization solutions, you see that the more we optimize, the cheaper it's getting. And this is mainly down, as I said, not to material costs, but to process time. So to how long it spends on the machine, and therefore how much of the machine capital cost is amortized, among other factors. And there are, of course, other factors to consider around operations costs, gas consumption, and so on. But broadly speaking, this is the effect you see, and it's quite logical. Even the most optimized Scalmalloy one is much more expensive than the milled aluminium one in this case. As I said before, we didn't pick a brake caliper because we thought it was a particularly good idea. It was more just to have an example. And I would say, looking at this, unless you really value weight saving, it's not a very good idea. But maybe you value weight saving enough, because weight saving is what you get in combination. So this Pareto front, just to understand, you have the part cost on this axis and the part mass on this axis. And this is the baseline. So the baseline milled part represents the minimum cost solution. The interesting thing here is, typically with machining, if you were to optimize the part for mass, but stick with machining, you would normally see that as you reduce the mass, the price would go up. So you would have a line in this orientation. Unfortunately, we didn't do that exercise. Maybe it's one to do, but you would have a line going in this direction. With the additive solution, it's the other way around. So you have your baseline design just printed by additive is far, far more expensive. If we had a maximum cost solution boundary, that would be it. But what we see is with optimization and then optimizing material as well, we actually see that with AM, we're on a different direction of optimization. When we save mass, we save cost. And so this is quite different to a traditional mindset that you might have in design, where normally you save mass, you're going to add manufacturing cost to that part. There's more effort involved. And I guess you could say, if we had the other line, you could look at the crossover and decide, where does it make sense? Is the gradient like this? Is the gradient like that? And you would get an idea of where the AM solution beats the optimized milled baseline solution. So this just to give you this idea. Now, of course, every case will give you a completely different answer in the end. I mean, it's very specific to the part you're considering. But this wasn't a case that we designed to make Scalmalloy look good. It's just a case we picked. And I think it shows quite effectively, at least, why in any case, optimization is very important for AM, regardless of material selection. You can see the effect of that. And if you also add a better material, you're going even further in a direction that many customers would view as being beneficial, because they like to save mass. If you're talking about aerospace, space, most moving applications, they worry about that, dynamic or otherwise. And then you're moving in the direction of reducing part cost. So 2 positives, I would say. So that was all I wanted to share with you today. I hope I didn't go too much over time as a result of the little glitch in the middle there. Just to leave you with a parting shot to prove that the welding thing I mentioned earlier is possible. Some of you may remember the Light Rider, which was a pretty cool development we made a number of years ago. And this is basically a Scalmalloy frame, but it was made originally, actually, at the time we only had an M290, so we had a small machine, and it's made out of multiple segments which were welded together. And you can see that you can achieve some pretty cool stuff. If you take Scalmalloy and you combine it with fabrication, you can make some pretty impressive things. Okay, so Angela, do we have some questions?
We do.
Okay, just while we get the questions up, just to point out that you can contact us on these. So if you have a pen and paper, you can write that down and contact us. So, questions. In terms of AM buildability of such designs, such as Scalmalloy, how would you grade it? Is it a very forgiving process, easy to build, i.e. high aspect ratios, low residual stresses, overhang angle, etc.? And how about process speed in comparison to Ti-64 and LSI-10? Good question, Alejandro. I hope I pronounced that correctly. So I would say in terms of forgivingness of the process, it is very forgiving in terms of the fact that it has this very high ductility, and prior to heat treatment, it has a very low yield strength and very high ductility. And when you come to dealing with residual stresses in the AM process itself, having what the ideal material is one that when you put it down, it has a really low yield strength, preferably a low modulus as well, but that's not always possible, and very high ductility. Because in that situation, you can deal with the thermal stresses across the plate for large parts with very small plastic deformations locally in the supports without failure. And that enables you to build up really quite big parts. And we've built some huge parts in Scalmalloy without encountering issues like cracking. So if you compare it to titanium, it's amazingly good to build with, because for an equivalent large part, it's just much, much easier without a heated build chamber and so on to still achieve a good result. In terms of the other questions, process speed in comparison, I mean, it all depends on your parameter set. If you optimize for surface finish, of course, this tends to degrade your process speed versus optimizing for productivity. But I would say it's very much in the same range as aluminum silicon 10. Generally, the process speed is mainly dictated by the thermal conductivity, specific heat capacity, and so on of the material, and it's not that different. So in the end, you end up with relatively similar results, although interestingly, the process parameters are not identical. So obviously at the start with Scalmalloy, we tried just first to test, run it on aluminum silicon 10 parameters. It didn't work that well, and we did have to tweak the parameters quite a bit. But this might be more things like surface tension of the melt pool and so on that forced us in this direction. But the end result in terms of build-up rate is very, very similar. So a question from Christoph, my good friend Christoph Wielenberg. Hi John, you showed a lot of applications for Scalmalloy. Where do you see ALSI-10 more competitive than Scalmalloy? I would say this could be the case in things where you don't really have structural requirements and you don't plan to do any optimization. So one reason I gave the example of the baseline solution printed in aluminum silicon 10 versus the milled one is to say that's logically what you would do if you were just printing exactly the same geometry and there was no stress requirement. So as soon as there's no strength requirement for the part, it doesn't make much sense to use a more expensive powder, obviously, because you're not exploiting the benefits. And equally, there's very limited scope. In the case of, let's say, applications, unless you get into certain applications which may not have a strength requirement, which are quite complex, in many cases it's quite difficult, other than in prototyping, to use it. Even some cases where people think it's not strength related, like for example, in a heat exchanger or something like that, in general, you're still running with a pressure. It's a pressurized system. And the thinner you can make the wall, the faster the response rate to temperature changes. So of course, having a higher strength is enabling you generally to run a higher pressure at a thinner wall. And so there can still be some benefits there. Jean-Pierre is asking, why is the cost of Scalmalloy powder more expensive than titanium powder? In reality, Jean-Pierre, this is, I would say entirely, almost entirely, even entirely due to the cost of scandium as a raw material. So in Scalmalloy, there's a very small percentage of scandium. It's less than 1%. But scandium is, I can't remember the figure, but it's an eye-wateringly expensive metal because it's produced in very low volume. It's actually not a bad material in terms of the fact that it's actually taken from, generally mined from the waste of other types of mining. So it's just the effort involved in extracting it, because it's in very, very small quantities everywhere, pretty much in the world. And you have certain countries where they have dedicated the effort to mining this, where they have slightly higher levels of deposits. But the effort involved in mining really drives that raw scandium price. And that's almost entirely dictating the effect, especially when you take into account the fact that with powder production, you always lose some percentage of the powder because it's the wrong size range. And so this is, of course, compounding the issue. I'm just looking through if there's any others I can easily answer. So Eldar is asking about, is there a difference in terms of post-processing, heat treatment, surface finishing for the optimized parts of different materials in the given case? So in terms of heat treatment, there is some difference, I would say, with aluminium silicon 10. The heat treatment, depending on which heat treatment you apply, is actually quite similar to Scalmalloy. I would say Scalmalloy is a slightly longer heat treatment at a similar temperature. So it may be marginally more expensive, but it's a very minor factor in the costs, as you can see. And in terms of surface finishing, it would be very similar to aluminium silicon 10. The one thing we have observed as an advantage of Scalmalloy over aluminium silicon 10 is, in fact, with chemical etching, for alkali etching, it's much more effective than with AlSi10, where you have silicon in the alloy, and that can lead to some more tricky etching processes to achieve a good result. Hendrik, I guess, have you already characterized Scalmalloy process by EBM? So we haven't at all tried it with EBM. One reason being that, at least to my experience of EBM, normally you're having to pre-sinter the powder and deal with relatively high build chamber temperatures. So you're normally, at least with the classic Arcam process, you're holding the temperature at above the stress relaxation temperature of the alloy. In this case, your cooling rate might be impacted by this relatively hot ambient process. However, whether that is a problem, I don't know. In the past, we never tried it, more because there were always some health and safety concerns around processing PRS, aluminium parts through a PRS system from EBM. Maybe that's improved. Maybe there are people working with aluminium on EBM today who might be interested to give it a go. I don't know of any today personally who have tried it. I think there's one more question which I can't answer, unfortunately, Gregory, but maybe email me and I'll try and find out, which is around how much Scalmalloy is produced by AppWorks in a year. Off the top of my head, I don't know, I'm afraid. So I will try and find out for you if you're really interested. But it's not, let's say I can answer the question, produced by AppWorks is 0 kilograms. So that's an easy question to answer, because in fact, we have 3 licensed material suppliers who produce the powder, and that was to try and get the price down and to have more economy of scale and so on with the process. So it's possible to source the material from these suppliers. So we don't produce any. So maybe I can answer your question, and I don't know how much they produce precisely, but I'm sure I can find out. But let's see. Okay, I think that's questions, Angela, the ones I can see. Yeah. Okay.
Perfect. Good. Yeah, thanks for the presentation, John. Really good to see that this, let's say, statement we made is not the truth, surprisingly.
Not quite the truth. It's not too expensive, but it's too expensive if you don't design for it. That's the point. If
exactly.
AM, it's too expensive. If you do design for AM, it's a great material, and it can save you a lot of money. That's maybe the message. If I do a sales pitch now, that would be the message.
Perfect. That's the take home, at least for everyone.
Yeah. Cool.
Perfect.
And thanks everyone for joining.
Thanks,
I quite enjoy these things. It's quite nice to get the questions on the chat and everything. And of course, feel free to email us if you have any more questions. I'm sure Angela will pass them on to me, and we can come back to you.
Yeah, I will. Yeah, perfect. Then thanks again, and thanks for everyone participating and for the good engagement. And yeah, we will hopefully see us all again next week. Next week is Wednesday, and not Thursday as all the other weeks, as we have this let's say second month of bank holidays in Germany, which is June. So we will shift to Wednesday, and it will be, according to the calendar, the last coffee break we will go for. But still a good one. So we will look into Hyperjoint and its applications, especially for motorsport. So that will be the topic for next week. So I hope to see everyone then back again next week on Wednesday.
She's like a teacher, isn't she?
Perfect. Yeah, good. And I wish everyone a nice afternoon, and talk to you soon, hopefully.
I wish Eliana a nice morning.
Yeah, right.
Cheers, guys. See you.
Everyone. Bye-bye.
Bye-bye.